This is FRM Part 2, Book 1, Market Risk Measurement and Management, and the chapter on the science of term structure models. As you know, in financial research, we're always trying to figure out what is the best interest rate to use to value some kind of a security. And virtually all of the term structure models present a way to either identify or to compute or to measure some interest rate so that we can discount future cash flows back to the present. Now, this is a pretty long chapter, and I've got a substantial number of slides. And you'll understand that when I show you all these learning objectives. Notice that there is a calculate, there is another calculate, there is an evaluate on here. And note, boy, this is a full slide of learning objectives. So there are lots of these. So let's go ahead and just quickly summarize what we're going to try to do here. Notice that first one. Calculate the expected discounted value of a zero coupon security using a binomial tree. We're going to use that first learning objective to kind of fit in to the rest of those learning objectives. We'll go ahead and extend it to some call options. We'll talk about risk neutral pricing and probabilities. We'll see what happens over multiple periods. We'll talk about some spreads, and then we'll talk about swaps. We'll even fit in the Black-Scholes-Merton option pricing model in the end. So let's go ahead and get right to it. And let's start with an introductory concept about this binomial tree. And so what I want you to do is I want you to look at that illustration at the bottom of the slide. Notice that there are some dots. There's one dot, then two, then there are three. And I want you to think about those as kind of like a timeline. So the node in red is time period today. So we're going to solve for the value of a security today. The two nodes in purple are possible paths. So this binomial tree means that we can start at the root and we can either move upwards or we can move downwards. And so the purple nodes are those two that are possibilities in the end of the first period. So time period 0 it is red, time period 1 is purple, and then what can happen at time period orange? We can either go up or down, or we can either go up or down. And notice we arrive at that same middle node there at time period 3. And don't let it stop right there at time period 3. We can go to 4 and then 5 and 6. I mean, we can have this gigantic binomial tree where we could have, imagine if we're trying to price that Walt Disney bond that was issued back in the 90s. It was a 100-year bond. And the fascinating thing about that one is if you do any research on it, Walt Disney indicated that he wanted to lock in a relatively low interest rate. And those of you who were adults who were paying attention to these things back in 1993, interest rates were way higher than they are today. And so I think that coupon rate is around 7.5% on that Disney bond. But imagine a tree that goes out for 100 years. Think of how complex all of those nodes are at time period 60 and 70 and 80. And by the way, you might be thinking, well, why hasn't Walt Disney called that bond? Well, it does have a call feature, but it had a delay called. He can't call it for 30 years, so he's got another, 5 or 10 years. Of course, when I say he, I really mean them. I'm fully aware that Walt Disney is no longer with us. Notice what I have on that last circle point there. Some kind of a complex network, and so that's really all I'm talking about there. Now, backward induction is a concept in which we are going to do something like this. So let's go ahead all the way out to the far right nodes. And if this is a fixed income security, what do we know happens on the maturity date of that fixed income security? We know that the bondholder is going to receive the par value or the principal amount of the bond. And if we assume that those par values are in increments of $1,000, then we know that we're going to get $1,000 regardless of which path that we take. Now, of course, this is not guaranteed unless it's a treasury security, and so we'll try to deal with risk as we move through this slide deck. But we still know that that promised cash flow is $1,000 at maturity, and then we can work back at each of those particular nodes in between today's date and the maturity date of the bond. And what are we going to get? We're going to get those coupon payments at each of those nodes. Now, in order to value the bond, we're going to discount them at maybe different interest rates. That's why this chapter is called something about term structure of interest rates. And that's really one of the great challenges of any one of these interest rate models, is to identify what is the appropriate interest rate for each one of those nodes. And we'll talk about that as we go through. All right, so quickly here, bonds are redeemed at par. We know that. Therefore, if we start at maturity, we fill in those values and we work backwards from right side to left side to find the bond's value at the desired node. So this is backward induction. We start with 1,000 and then we work our way back. We keep discounting them back to the present value. And we do that at different interest rates. And each of those interest rates is going to be a forward rate. What we do with this term structure, right? This chapter is called term structure. What we do is probably start with some estimate of spot rates or maybe par rates. Remember, we did all that in a previous video, and then we can convert those into forward rates. Now, in the chapter and in this slide deck, these forward rates are going to be given to us, which simplifies our life. Now, backward induction, of course, relies on this concept of no arbitrage opportunity, meaning that when we discount these things all the way back to the present, we get the current market value of that fixed income security or the derivative or whatever security that we're trying to price. Let's go ahead and take a look at an example. Let's suppose we have a binomial tree, $1,000 face value, 0 coupon bond, 2 years to maturity. All right, so notice there's our tree going to the right. So there's today, time period 0, end of time period 1, end of time period 2. We'll just call this a 2-year bond. And notice that no matter what interest rate path we take, whether we go from the 4.66 today up to 7.25 or down to 5.5, and then up or down, we still are going to get that $1,000, or at least we're promised to receive that $1,000. So that's the future value of the bond. And since it's a 0 coupon bond, there are no intermediate payments. We're not getting a coupon payment at the end of year 1. We're not getting a coupon payment at the end of year 2. Now, what I've done in the second circle point there is just to remind you of how simple the model is that we use way back in our undergraduate investments class. This is what we would do. We would say future value is 1,000, n equals 2, I equals, well, I just picked that first rate, 4.611. Maybe we could have picked another one. Payment is 0, solve for present value. And that was a simple application using our regular time value of money buttons on the calculator to arrive at a present value, right? And what we assumed back in the introductory investments class is that the term structure is fixed over the life of the bond, and that the interest rate or the yield to maturity is that 4.661% today, and it remains as such over the next 2 years. If that's true, well, then the bond price is going to be 9.12. But of course, what do we know? We know that we don't operate in a static environment, we operate in a dynamic environment, and so not only do interest rates change, but it's probably better to use a rate other than the yield to maturity on the bond inside of this model to reflect reality, right? All right, so let's use this tree to try to figure out the price, and let's try to figure out how we work back to the price. So what we're going to do is make a quick assumption here that the bond's market price is 900. Now, also, we're going to assume that if we buy that bond for 900 today, that 1-year rate is 4.66, right? So we can either have an interest rate path that moves up to 7.25 or moves down to 5.5. And so those have equal probabilities. All right, so how do we go about this? Let's go ahead and do the math, right? So we're going to start at the end. So let's start at those top 2 blocks of 1,000 and 1,000. We know that when we start today, if interest rates go up to 7.25, we're going to be sitting at 7.25 a year from now, and we know we're going to get $1,000 a year from now. Now, what could happen? What could happen between the end of year 1 and the end of year 2? That 7.25% could go up Now maybe it'll go up to 7.75 or maybe it'll go down to 6.75. Doesn't really matter because that's a forward rate. So all we're going to do, and because we assumed equal probability, is we're going to take the weighted average of those two, and the weights are equal. So notice what I have in the first circle point. There's our first math in this slide. We have a 50% chance of getting 1,000 and a 50% chance of getting 1,000 because they have equal probabilities. And we're going to discount that back at 1 plus that forward rate of 10725. So look at that 932.40, the result of that simple math. Just imagine placing that right above the 7.25% inside of that box. All right, now let's go and do the lower node at the end of year one. We're going to do the exact same thing. So we have the 50% chance of getting 1,000, the 50% chance of getting 1,000. So what does that mean? That's a 100% chance of getting 1,000, right? And we're going to discount that back at the lower forward rate, not the 7.25 in this example, in the previous case, but the 5.5. So notice I have divided by 1.055, so that gets us the 947. Now imagine putting that 947.87 right above in the box, right above the 5.5%. So what do we know? We know we're going to buy the bond today for 900, and what's happening is that we might be able to sell it a year from now for 932, or we might be able to sell it a year from now for 947. So those are the values of the bonds at the end of year one. And what's going to happen is that we're going to discount those back to the present again. And if we discount those at the 4.661%, we get the $900. So notice we take 932 times 50% and 947 times 50%. And so we arrive at that $900. Now this kind of looked like it was magic because if I go back here, I said, hey, let's just suppose the price of the bond is $900. But the reality of life in forming this interest rate tree is that you identify those forward rates that are going to result in the current value being equal to the price of the bond, the market price of the bond. That's that no arbitrage condition. Now, how about if we switch over to derivatives? All right, so look at that first block point. No arbitrage pricing approach for valuing a derivative consists of three main steps. So we can do this with a derivative on a zero coupon bond. And what we're going to do is use a replicating portfolio to do this. And this idea of a replicating portfolio is really, really cool. It goes all the way back to our conversation on put-call parity. Remember, there's a link between and among the equity markets, the fixed income markets, and the derivative markets. And you can use this model to try to determine whether or not there's an arbitrage opportunity in one or many or all of those markets. And so what we're going to do is rely on the simple fact that there's not. And we can have a replicating portfolio. So we can replicate the payoffs of an option using some other security. And I'll show you how that works here. So here are the three steps, and we'll work through these in an example. We're going to describe the model and look at those future payoffs. We're going to construct a portfolio of underlying assets that has the same random payoff as the derivative and set the price of the derivative equal to the value of the replicating portfolio. So the math of this is going to be fairly simple, but all we're doing is saying something like, look, if I say to you, a year from now, I'll pay you $5 or I'll pay you $0, right? That's an option depending on some underlying facts that we don't really need to know about. And so what do you have? The value of that little arrangement between the two of us is going to be the present value of the 5 and the present value of the 0 depending on interest rates. Well, we could buy a bond and we can short a bond that's going to have a present value that's equal to the same present value in that derivative. And that's what the replicating portfolio tells us. All right, pricing a call option on a zero coupon bond using a replicating portfolio. All right, so consider a call option on a $1,000 par value of a 0 maturing at time period 1. The call option gives the owner the right, but not the obligation. Of course, that's the call option. That's our definition, to buy the underlying bond notice the exercise or the strike price I have in this example of $9.75. We have a 6-month option, right? So the bond matures in a year, but we have a 6-month option. All right, we're given some interest rates there, 5 and 5.3%. And 6 months from now, those rates will either be up or down, 6 or 4%. Both 6 or 4%, both outcomes are equally likely to occur. Let's go ahead and assume semi-annual compounding here, and let's figure out what the price of that call option is going to be. All right, you ready for this? All right, let's go ahead and describe the future payoffs. All right, so if the 6-month rate on date 1 turns out to be 6%, the upstate, the price of the 6-month zero will be, and there's the calculation there, right? We're going to discount that $1,000 at 1.03, half of 6%. There's our semi-annual compounding. It's going to be worth $970.87. All right. In this case, the right to buy the zero at $9.75 will be worth $0, right? So why would you exercise the option to buy the 0 coupon bond at $9.75 when you can just go out and buy it for around $9.71, right? So that's an out of the money option. So there'll be no point in exercise the option on that date, right? All right, if the 6-month rate, on the other hand, turns out to be 4%, then the price of that 6-month zero will be $9.80. So we discount the 1,000 at 1 plus the 2%, right? Semi-annual compounding again, and we get $980.40. All right, do you see what's going on here? The price of that fixed income security a year from now is going to be either the 970 or the 980, right? I'm doing a little bit of rounding there. In one case, the option has value. In another case, the option does not have value. All right, so when the interest rates fall down to 4% in the down state, then that option is going to have, and look at it, it's right there at the bottom, $5.40 of intrinsic value. All right. So there's our little timeline. There's node 0 and there's node 1. So we've got the 970 going up. We've got the 980 going down. And the call is worth 0 in the upstate, and the call is worth 540 in the downstate. All right, so those are describe the future payoffs of the underlying assets across those different possible states. So there's the payoffs for the bond, and there are the subsequent payoffs for the option. Step 2, what we're going to do is construct a replicating portfolio. We're going to construct this replicating portfolio at time period 0. We're going to buy a 6-month and 1-year zero coupon bonds that will be worth $0 in the upstate and $5.40 in the downstate. All right, so we're going to just put together a couple of equations here. And look at this circle point. We're going to have the face value of the 6-month zero plus the face value of the 1-year zero. And of course, that has to be a present value, right? So we're going to divide by 1 plus 3%, and we're going to force that to be equal to 0. So notice at the top circle point, I've got face value of the 6-month plus, now that's 1, right? There's an implied 1 there. 1 times the face value of the 6-month plus 97% of the face value of the 1 year. We're going to force that one to be equal to 0. And then we're going to do the same thing for the downstate, and we'll divide that face value of the 1-year zero by the 1.02%, right? And our equation is 1 times the face value of the 6-month, which is the same as the top equation, plus now we've got 98% of the face value, and that equals $5.40. And if you do the simultaneous equation solving there, you get F1 and F2. And so note what's happening. Face value of 1 is 568. The face value of the 6-month is 551. So what we're going to do is we're going to take the long position in the 1 year, and we're going to take the short position in the half year. And then what we're going to do is we're going to just discount both of those, right, at the 1.05 and the 1.053, and we're going to get $1.02. All right, so notice the bottom line there. A portfolio of the underlying riskless asset replicates the call if it satisfied two equations. Upstate portfolio payoff equals the upstate call payoff. Downstate portfolio payoff equals the downstate call payoff. And so notice what we did back here. We used those simultaneous equations based on the assumption and the replicating payoffs that we had in this model here. And that goes back to our design of the problem, which goes all the way back to here. And so note, the 6-month spot rate was 5 and the 1-year spot rate was 5.3. So let me just swing back here just to remind you. And you can pause this if you want to, just to make sure you can do the math. When we priced the call option, we used that 5% and that 5.3% that we had in the spot rates a couple of slides ago. How about if we compare these? Here, let me go back here just quickly too. Notice in this case, we had an up of 6% and a down of 4%. And in this model and the one that we did previously, when we computed the price of that zero coupon bond over 2 years, we were assuming that they were equally weighted, that we had an equal probability that the path was up and an equal probability that the path was down. So that, of course, was 50%. But the question then becomes, geez, does everything have a 50% chance of occurring? I mean, if I flip a coin, 50%, that's pretty obvious. But if I go over to my TV and turn on a business news channel during the afternoon, is there a 50% chance that the Dow is above what it was yesterday? Is there a 50% chance that the price of an option is above what it was yesterday? Probably not. All right. So notice what I have in that top block point up there. Every single event has some probability of occurrence, right? That's what we call the true probability. And many, many times we don't know what that true probability is. So I have in bold, the probability for an up and down for those down states was half. However, these probabilities may or may not produce an expected discounted value that exactly matches the market price of the bond. Because what we do is we assume that those are true probabilities. And we probably don't know what those true probabilities are. All right, you ready for this one? So let's look at the risk neutral probabilities. These are probabilities that force the expected discounted value of the bond using the model, using these term structure models to be equal to the market price. So these are probabilities of potential future outcomes that are adjusted for risk. And what we call the difference between the risk neutral probability and the true probability, that's known as an interest rate drift. All right, so let's spend a minute here talking about this risk-neutral pricing. It's a technique that modifies an assumed interest rate process. It's a contingent claim that can be, a contingent claim that can be priced without having to construct and price its replicating portfolio. So we had a little bit of complexity when we did that replicating portfolio. Now, it was relatively simple in that example that we used, but it can get much more complex. We like this risk-neutral pricing because in the binomial option pricing formula, it's interpreted as the discounted expected value. Of course it is. All right, how about if we extend this to multiple periods? I think there was one learning objective that asks us to do this. All right, let's go ahead and value an option on a fixed income instrument using a binomial tree with multiple periods. All right, so what we're going to do is we're going to price the bond at each node using those projected interest rates. All right, so we have time period 0, so we'll price the bond at time period 1. Up and down states, we'll price the bond period at time period 2. Up and down states, up and down states. We'll do all that. What we'll do is calculate the intrinsic value of the derivative at each node in the maturity. So sometimes the option, or any derivative really, but since we're doing an option here, Sometimes the option will be in the money, sometimes it'll be out of the money. So if it's in the money, it'll have some positive intrinsic value. If it's out of the money, it'll have a 0 intrinsic value. And then we're just going to discount, working backward through the tree. Those 3 basic steps. Now let me define the recombining tree versus the non-recombining tree. What I want you to do is I want you to focus on that time period 0, that time period 2 over on the left-hand illustration. You see the 5% on that middle node? How can we get to that 5%? From time period 0, we can either go up to 5.2 and then down to 5. We get to the 5%, right? Or we can start at time period 0 and go down to 4.75 and go back up to the 5%. So that recombining tree arrives at the same node right there in the middle for time period 2, and then subsequent if there were more time periods out there. Now, look at the illustration on the right. Notice that we don't arrive at that 5%. If we go up to 5.25, maybe we go down to 5 or up to 5.2, right? So there's the 5. But if the path leads us downward and we go down to 4.75, then we only go up to 4.85, not to 5. So there's not a link at that node. There are 2 separate nodes. That's the nature of the non-recombining tree. And notice the block point down there, note. Let me read this like I'm some formal dude out there. Practitioners tend to avoid non-recombining trees because they are, oh my gosh, let's just not even read that. It's really difficult to decide how you're going to handle those differences in those interest rates at those particular nodes. How do you implement them so that you can maintain that sense of no arbitrage? It's pretty difficult mathematically. All right, we did fixed income securities. We did an option. Let's go ahead and do a swap. So we have this swap. We're going to swap a floating rate for a treasury rate, such as the 10-year rate. All right, so we're gonna swap a floating rate for a fixed rate. So this is a constant maturity swap, right? CMT. That T stands for the treasury. All right, so let's go ahead. Let's assume a notional principal of $1 million. So that's what $1 million is in the numerator. And that number could be 10 million or 100 million. We divide by 2 because the swap pays out every 6 months. Then all we're going to do is we're going to make a bet, right? We're going to bet that the floating rate is going to be different than that fixed rate of 6%. And so depending on whether we're paying floating or receiving floating will determine whether or not we're going to win. I mean, let's face it, if we're receiving floating, what do we want? We want that floating rate to go way up. We want it to be 10% or 12% or 80%, right? If we're receiving the floating rate, if we're paying the floating rate, then we want to pay a lower rate than 6%. Notice this, 70% risk neutral probability of an increase in the 6-month spot rate and a 60% risk neutral probability of an increase in the 1-year swap rate. Calculate the value of the swap. Let's see how simple this is here. All right, so let's go ahead and put together our swaps. So our interest rate path. So here we're starting out at 6%. We've got a 70% chance of up and a 30% chance of down, in which case the interest rates will be either 625 or 575. Then once we're at the nodes, then we have a 60% chance of going up and a 40% chance of going down. Notice this is a recombining tree, so we're meeting in the middle over there at 6%. So remember what I said, in the very first slide, there's time period 0, there's time period 6 months from today, there's time period 12 months from today. And there is our interest rate path with the appropriate risk neutral probabilities, right? So that treasury rate is 6%, and that's why we have that 6% at time period 0. And then we've made some estimates about those interest rates going forward. All right, in 6 months, then those payoffs are going to be, are you ready for this? What's going to happen? I'll swing back and forth here. So a year from now, the interest rate either could go up or down, right? So if it's 625, this is good news for the payoff of the receiving floating. So that's 1250. And then if it goes down, let me go back here. If the interest rate goes down, then the payoff is going to be a minus 1250. Now, the reason those two numbers are the same, the 1250 positive and the 1250 negative, is because 625 minus 6 and 575 minus 6, the absolute values, those are the same numbers. So we get that 1250. And so remember, we could have said that the interest rate going up could have been 6.33 and the interest rate going down could have been 6.79 or some other number. So that those two numbers, the 1250s, would not have been identical. All right, so all we're going to do is, kind of the same thing as we move forward. We're going to say, well, the interest rate could continue to go up, or it could go back to 6%, or the interest rate could go up to 6%, or it could continue to fall down to 5.5%. And so this is all we're doing. We're taking the 6.5 minus the 6 minus the 6, the 5.5 minus the 6. So this works exactly like, it works exactly like a call option. You just take the difference between the current price and the exercise price, and you can compute those payoffs. And since we're going up, let me go back here. Since we've gone up by another 25 basis points and so these numbers are going to be the same. All right, so we have in 6 months, we either have a positive 1250 or a negative 1250. In 12 months, we either have a positive 2,500 or a negative 2,500, or we have zero. If the 6% and the 6% are the same number, then there's no payoff, right? That's $0. Think of that as kind of like an at-the-money call option. All right, so what are we going to do to try to value this thing? All we're going to do is take the present values, right? So we're going to say 2,500 times the 60% plus 0 times the 40%, right? Let me go back here. That's in the 12 months, the 25 and the 0, right? So if we do the math, we get the 2704, and if we do the math on the downward, we get the 2222. And don't forget to add the 1250 and subtract the 1250 in there when we're taking that present value. And then we need to discount it all the way back to the present. And so notice we'll use those current risk neutral probabilities, the 30% and the 70%, and we'll use that original 6% divided by 2, of course. So that gets us a price today of 1190.86. So here's a summary slide of what we were doing. Notice on the far right block, there are the payoffs, and then we're just discounting those back. And discounting those back using the risk neutral probabilities. And of course, if you think about it, if you put 50% in there at each one of those nodes, we're going to get a different price. So these risk neutral probabilities add value to, and they add precision to the value of that swap today, 1190. How about an option adjusted spread? This is the spread that makes the value of the present value of those projected cash flows equal to the current market price. What we're going to do is we're going to add this spread to that term structure, right? So that the price of the model is equal to the market price using those risk neutral rates. All right, let's take a look at a quick example here. Let's suppose that the market price of that swap was $11.89. And what did we say that price was? $11.90. So mathematically, that's 94 cents less than the model price. Let's just go ahead and round that to $1 here as we're thinking about this. All right. And so let's go ahead and use some kind of a model to come up with an option adjusted spread is going to be 10 basis points. All right, I'll tell you about how to get that here in just a second, but this is what we're doing. what we're going to do is we're going to add 10 basis points to the present value calculations that we did earlier, right? So notice that I have in the denominator there 1 plus 0.0635. It used to be 0.0625. So I add the 10 basis points. And then look in the second denominator, it used to be 0.0575. I added 10 basis points, so now it's 0.0585. So we're adding that option adjusted spread. And what we do is we get the 2703.84 and a minus 2221.58. All right, and so what are we going to do? We're going to weight those by their risk neutral probabilities, and then add another 10 basis points to that original discount rate today, right? That was 6%. Notice we're dividing by 0.061, and we get the 1189.92. All right, so what am I saying here? I'm saying something like, look, the model gave us 1190 based on this term structure, right? Well, what happens if the price is not 1190? Do we say that our entire term structure is wrong? Well, we might, but we may use this term structure to compute the price of what's known as this option adjusted spread so that we get the 1189. And so notice what happens. Discounting at the risk neutral rates plus the price, plus the option adjusted spread is going to give us the model equal to the market price of 1189.92. So look at that blue box down at the bottom there. The mathematics of this are probably important, but this thing here is probably something that you ought to memorize. If the option adjusted spread is positive, the market price is less than its model price. So we probably want to buy that security. On the other hand, if it's negative, it is trading richly. Maybe we don't want to buy that security, or maybe we'll want to short it. All right, so the question then becomes, notice that our intervals were, we had time period 0, then we had time period 1, and then time period 2 and 3, and then we chopped it into 6 months. Boy, do we need to chop it into quarters? Do we need to chop it into months? Do we need to chop it into days, into hours? So in practice, time steps smaller than 6 months are desirable for two main reasons. I mean, what are those things? I mean, let's think about this. It's not uncommon to find a security or a portfolio of securities that make payments in uneven intervals from the starting date. I mean, you could have a portfolio of 3 bonds and they might pay interest every 6 months, but you might be getting a coupon payment every 2 months. One bond, then the next bond, then the next bond. Yeah. The rigidity of 6-month steps means that you can only value those things in 6 months. So think about this, you have the node and then you have these 2 nodes up here. So you can only do it in those 6-month intervals. All right, so notice what I have in bold under the second circle point. Reducing the step size populates the tree with rates sufficient to price the contingent claims with a healthy level of accuracy, right? That's what we're trying to do. Now, of course, if we've got all these different nodes in there, then it's going to require tons and tons of computations. And I've done this many, many times. I mean, some of these interest rates, you have to go out to, 6 or 7 or 8 or 9 significant digits so that you don't have the same number over and over again. Black-Scholes-Merton, which is one of our favorite models. I know it's one of my favorite models. All right, so how about 3 assumptions that do not apply to fixed income securities? All right, you ready? Bond prices do have a maximum value. The upper limit occurs when interest rates equal 0, so that the bond is priced at par value, right? So for coupon bonds, then this upper limit is the sum of the coupon payments and the par value. Yes, when you guys use that Black-Scholes-Merton option pricing model, you assume some risk-free rate, and we assume that it is static, that it is constant over time. What do we know? Those changes occur, interest rates, those changes occur regularly. And it also assumes that standard deviation is constant. So when you use the Black-Scholes-Merton option pricing model to price fixed income securities, there are some issues that you need to be concerned about. And I think that takes us through.